we present Robustness via Retrying. Video prediction planning enables robots to learn complex skills using autonomously collected data. The user specifies one or more pixel goal position pairs in the start image. Then the planner finds actions which the video prediction model predicts will move pixels closest to their goal. Since the system is not tracking the object, it cannot recover when its original actions do not go to plan. If the robot can keep track of how the current scene relates to the initial and goal scenes, even an imperfect controller can continue to retry the task and eventually succeed. Off-the-shelf trackers offer a possible solution, but they tend to be fragile. They often fail due to occlusions, large movement, or clutter. In this example, the robot arm moves in front of the object, which causes the key point tracking to fail completely. The goal of this work is to enable self-supervised closed-loop visual control to improve robustness by enabling the robot to retry indefinitely. Our approach is to learn to track pixels in a self-supervised way, and to use the signal to replan adaptively at every time step. The video prediction model predicts future frames given the current image and proposed actions, while the tracking model determines where the goal and point of interest are located in the current image. At test time, a start image and optionally a goal image is passed to the controller, which performs closed-loop visual control. The training data is video and telemetry of the robot randomly pushing and grasping objects in a bin. The network is trained by warping images from arbitrary time steps along a trajectory to match each other. At test time, the network tries to find pixels in the current image corresponding to those marked in the start and goal. The register points are now used in the cost function for planning. Registration is easier when the object is closer to the position in the registered image. We propose a method to fuse both the forward and backward registration costs, weighting them by how accurate the registration is estimated to be. On the left, we can see the start and goal images with the designated pixels marked in red. On the right, we can see a red cross where the registration network estimates the start point. Similarly, the goal is in blue. The opacity of the crosses indicates the trade-off between the registration of the start and goal. As you can see, this tracking still works when the object is perturbed. To summarize, the user provides an image of the goal and position of the object in both the start and goal images. At every time step, candidate action sequences are rolled out with the video prediction model. The robot executes the first action of the sequence with the lowest cost. After executing the action, the registration network finds the location of the pixels corresponding to the designated pixels marked in the start and goal images. Updating the pixel positions allows our method to retry indefinitely until it succeeds, allowing for a high degree of robustness. Our benchmark consists of 20 different real-world tasks. In the relevant region, our method outperforms both baselines. We specify 3D tasks by providing images and pixels in multiple views. Note that grasping behavior emerges automatically as a result of general-purpose planning. In principle, the agent is free to use pushing as well, but the planner finds grasping to achieve lower cost. Replanning is also crucial for grasping success. In this example, the object is removed from the robot's gripper after the initial grasp. Thanks to our proposed registration network, the robot retries the grasp, thus enabling robustness. We show that closed-loop visual NPC can solve challenging manipulation tasks where an object needs to be relocated while avoiding an obstacle. By defining an additional cost-penalizing movement of pixel on the obstacle, the planner finds trajectories that avoid it. We perform a similar benchmark, but allow the robot to use grasping to achieve its objective.